all the stuff we were talking about in this unit are hopefully trivial to you. But we are now getting to the new things that come with the methods 3.4, which is about the solution spaces of linear systems. Of course, you learned how to solve linear simultaneous equations since primary school, perhaps. But can we solve any linear system? For example, the following 2x2 system with these coefficients can be solved quite easily. And the solution is actually visualized as the point of intersection of the two lines. Because in this case, the first equation describes a line in the Cartesian plane. The second equation describes another line in the Cartesian plane. Therefore, the system of two equations is solving for the intersection between the two lines in the coordinate system. Therefore, several situations can happen if you are given two equations and try to solve the system. The first one is that if the two lines or the two equations describe parallel lines, so the lines described by the given equations will never intersect, and therefore the system will have no solution. Otherwise, most commonly, the two lines are not parallel, and therefore there will always be a unique point of intersection, which always corresponds to the unique solution somewhere here, or anywhere, basically. But if the two lines are parallel, yet that they are literally the same line, then obviously the two equations correspond to a set of points which coincide everywhere. So this particular system will have infinitely many solutions, because infinitely many points are on both equations or on the line described by both equations. The real matter is, how can we treat this situation algebraically and analyze the situation? Let us now consider this most general 2x2 linear system. The first equation has coefficients a11 and a12, where the a11 really just indicates row 1, column 1. And this one indicates row 1, column 2. Now, the second row, of course, gets a21 and a22. So these are the coefficients related to x and y. And the right-hand side are just constants called C1 and C2. Since the existence and uniqueness can be considered as whether the lines intersect, then let us write the lines in its slope-intersect form, which is simply a rearrangement of this system. Notice that the gradient of the two lines are m1 and m2, which are written in terms of a11, a12, a21, and a22. And recall that from the picture, if the two lines are parallel, i.e. they have the same gradient, then it's possible that they have no solution or have infinite solution, but never unique solution. So, in order to have unique intersects, then we must have m1 not equal to m2. Therefore, substituting in the values of m1 and m2 we found from the expression of the system, we know that the system can only have a unique point of intersection or a unique solution if a11, a22 minus a12, a21 is not 0. Furthermore, however, if the lines do have the same gradient or the same slope, such that a11, a22 minus a12, a21 is 0, then the system leads to two parallel lines, which may correspond to no or infinite solutions. In particular, if the two y-intercepts are the same, such that C1 upon A12 equals to C2 upon A22, then the system has infinite solutions because they are going to be literally the same line. Whereas if that's an inequality, then we get two different parallel lines, such that they will have no solution at all.